Okay, we're going to go ahead and get started on problems 2 through 9 from Chapter 3, Section 1. So let's go ahead and do problem 2. So problem 2 says you have an FM radio station found at 103.1 on the FM dial, and it broadcasts at a frequency, so let's go ahead and write this down as we get them, frequency of 1.031 times 10 to the 8th s to the minus 1, which we also know is hertz, right? So we can write that as 1 over s. And we always know c, and we're going to go ahead and write that in, 2.998 times 10 to the 8th meters per second. And it's asking for what is the wavelength in meters. So this is what we're looking for. And of course we have our formula, which is C is equal to wavelength times frequency. And so if we want to solve for wavelength, we need to isolate that. So we're going to divide both sides by the frequency, and you can see those cross out. And so you get C over frequency is equal to wavelength. Now that's the formula we're going to go ahead and use for this problem. Now we just solve these, plug these values in. For C, we have 2.998 times 10 to the 8th meters per second, okay, over the frequency, which is 1.031 times 10 to the 8th, 1 over s. And that's equal to a wavelength. So now, solving for this wavelength, we go ahead and we divide these out, and you'll get a value of 2.908 meters when you plug them into the calculator. And that's simply your answer for the first one. And remember, these cross out, right? Because you have denominators within your numerator and denominator, so those will both go ahead and cancel out. And then that leaves you with m over 1, which is the same as m. And so there's your answer. You've got 4 sig figs and 4 sig figs, so you have 4 sig figs in your answer. Okay, that's problem number 2. Let's take a look at problem number 3. And number 3 says you have FM 95, a FM radio station that broadcasts at a frequency. So this is going to be a very similar problem again. Here we have a different frequency, 9.51 times 10 to the 7th, 1 over s, or hertz. In this case, 95.1 megahertz. And what is the wavelength of these radio waves in meters? So we're looking for a wavelength again, but we do know C. C is 2.998 times 10 to the 8th meters per second. And again, just as the last time we used the same formula, C is equal to wavelength times frequency. We want to isolate wavelength, so we're going to divide both sides by the frequency. And so we get C over frequency is equal to wavelength. And so those cross out. So now we plug it in, just like last time. So you get 2.998 times 10 to the 8th meters per second over 9.51 times 10 to the 7th, 1 over s. Again, these cancel out, so it's going to leave you with meters over 1, which is meters. And then you divide these two values here, and you get 3.15 meters. And of course, you only have 3 sig figs because you have 3 there, and you have 4 sig figs there, so you're going to go with the smaller one, 3. So your answer is going to be 3.15 meters, and that's problem 3. Moving on to problem number 4. Okay, 4 is you have a bright violet line that has a wavelength of 435.8 nanometers. So wavelength is 435.8. Let me fix that dot there. 8 nanometers. In the emission spectrum of mercury vapor, what amount of energy in joules? So we're looking for energy. What amount of energy in joules must be released by an electron in a mercury atom to produce a photon of this light? Alright, so there's a couple things here. We have the two formulas. C is equal to lambda nu, and energy is equal to Planck's constant times nu, frequency. And again, in both cases here, you have those units in common frequency, which in this case we don't know. But we do know H. H is always going to be 6.626 times 10 to the negative 34th joules seconds. That's Planck's constant. And then C again is 2.998 times 10 to the 8th meters over seconds. So if I look at these two, again, we want to solve where we only have one unknown. So I know what the value of C is. I have wavelength here. I know what that is. Frequency, I don't know. Looking on this side here, I don't know what the energy is. We have a question mark there. We have a question mark for the frequency. Oops, excuse me, that should be a question mark. That's a question mark, and we do know Planck's constant. So here we have two unknowns, and here we have one unknown. So we can clearly solve for this formula first, which will give us the frequency, and then we can go ahead and plug that in as the value over here, multiply it by Planck's constant, and get the energy. So let's go ahead and do that here. Solving for frequency, we would have C is equal to wavelength over frequency. We want frequency isolated this time, so we're going to divide both sides by lambda. So you get C over lambda is equal to frequency as those cross out. And so let's go ahead. I'm going to do that over here. 2.998 times 10 to the 8th meters per second over wavelength, which is 435.8 nanometers. Now we know nanometers are the same thing as saying 10 to the negative 9th meters. And that's going to be equal to the frequency. So again, that's m over 1. So we divide those, but you can see clearly here you have 1 over s, and here now you're going to have 1 over 1. So your label is going to be 1 over s, which is good because that's a good unit for frequency. And so we divide these, and we get 6.879 times 10 to the 14th. Okay, and that's keeping in account for our 4 sig figs here. Now, we need to plug that in. Like we said, we're going to plug it into the value for frequency and Planck's constant, times Planck's constant, and this formula here. So now we know E. Actually, I can write this in here since I now know that this is 6.789 times 10 to the 14th. 1 over s. I can plug that in. So you can see now we have H and we have frequency. We can solve for energy. So I'm simply going to do that. It's going to be Planck's constant times frequency to the 14th 1 over s. Okay. Oops. And so let me put that back up. For some reason I bumped it. Okay, so the seconds cancel out there, and I guess I got a different color. That's fine. We'll finish it up in this color. And so the seconds cancel out, so your label is clearly going to be joule, and this is going to be your final answer anyways. So you get 6.626 times 10 to the negative 34th times 6.879 times 10 to the 14th. And when you multiply those, you get this value that comes out to be 4.558 times 10 to the negative 19th joules. And that should make sense. That should make sense. Okay? And that will solve problem 4, this being your answer. Okay? Now let's go on to problem 5. Maybe? Change that to black. And let's go ahead and screen options. Let's see here. It's not allowing us to erase the ink on the screen, so let me see if I can. Oh, that's right. I wouldn't let it discard it. So let me go ahead and add a slide in real quick here. Go back out. And let's click File. Oop, let me go here. File, Home, New Slide. Let's do that. Okay, now we're in business. So let's go back on. Change that color again. Every time I get off, it changes back to red. It likes red. So let's go to number 5. So light with a wavelength, you have 614. So wavelength, again, 614.5 nanometers. Looks orange, it says. And when you look at these, usually when you get wavelengths like 7 times 10 to the, what are they, around 14th or so? Yeah, 7 times 10 to the 14th, that's usually around red, and 6 times 10 to the 14th around orange. 5 times 10 to the negative 14, or 10 to the 14th is usually around yellow, and so on and so forth as you go through your Roy G. Biv. So anyway, this looks orange at around 600 nanometers. And what is the energy again? So it's asking for energy in joules per photon of this orange light. And then once you convert it to EV as well, electrovolts. So let's go ahead and solve this again. We know C is 2.998 times 10 to the 8th meters per second. And we know H is Planck's constant, 6.626 times 10 to the negative 34th joules seconds. And we don't know frequency again. So we're kind of in a similar boat as to what we were in last time, where we had these two formulas. And again, in both cases, we don't know the frequency or the energy. We don't know the frequency, but we do know C, we do know wavelength, and we do know H. So this is pretty much an identical problem to what we just did, with just a little twist on the back end. So again, let's go ahead and solve this. So I want frequency by itself, so I'm going to divide both sides by wavelength, and that's going to give me wavelength, C over wavelength is equal to frequency. And now I plug those values in, 2.998 times 10 to the 8th meters per second over the wavelength, which is 614 nanometers. And again, you could just write 614.5 times 10 to the negative 9th meters over 1, and that's going to be equal to the frequency. Now, those cross out. You can have 1 over S again, and 2.998 times 10 to the 8th divided by 614.5 times 10 to the negative 9th comes out to 4.879 times 10 to the 14th 1 over S. So that's now our value for the frequency, which I can go ahead and write in here. That's 14. And now I can plug it in over here times Planck's constant. So let's do that over here. H is going to be 6.626 times 10 to the negative 34th joules seconds times the value we just calculated, 4.879 times 10 to the 14th 1 over S. And so when we plug this out, our seconds cancel, we get joules. And when we multiply them, we get this value of 3.233 times 10 to the negative 19th joules. Okay, then it asked us to convert it to electrovolts. So it tells us if you have the energy, now we know the energy is this. Okay, if you have the energy, there's this conversion for electrovolts, which is 1 eV is equal to 1.602 times 10 to the negative 19th joules. So to convert it, you simply, let's do it the old-fashioned way, we'll plug it in our matrix. So that may make some of you feel more comfortable. Over 1. Okay, now it's telling us we have joules on the bottom, right? So we have 1.602 times 10 to the negative 19th joules, because again, we had to bring our label down. So joules is going to be on the bottom, and the conversion factor, 1 electrovolts right here. And again, this is just a conversion factor just like normal. So those cross out, and so you end up with 3.233 times 10 to the negative 19th divided by 1.602 times 10 to the negative 19th. Let me write that just in case so nobody gets lost. So remember, we multiply straight across the top, straight across the bottom, labels EV. And so you divide those two values and you get a value of 2.018 electrovolts. And that is that answer. And that's problem 5. So let's take a look at problem 6. See if we can do this. Screen, erase all ink on side. Voila. Get the hang of this. Okay, heated lithium atoms emit photons of light with an energy. Okay, so here we know energy. Energy is equal to 2.961 times 10 to the negative 19th joules. That's a 9. It's a terrible looking 9, but it's a 9. 2.961 times 10 to the negative 19th joules. Calculate the frequency. It wants to know the frequency and the wavelength. Ooh, 2 pieces. Of one of these photons. And then ask for what is the total energy in 1 mole of these. The color of the light. So I'm not overly concerned about the color of the light because, like I said, I can give you the ranges for that later. But let's go ahead and do this problem first. Again, we always know H because that's Planck's constant, and we always know C because that's the speed of all electromagnetic radiation. Okay, so what do we have to work with here? We've got E, we got the two formulas again because that's really all we've been working with. We know E. We know H. So we don't know frequency, but we can solve for that. And so this time we're going to go a little bit backwards. We know that. We don't know this. We don't know this. So if I solve here for frequency, I can then plug it here in, and then I'll have two pieces, C and frequency, and I can solve for wavelength. So to rework this formula here, you're going to have E is equal to H times frequency. So we want frequency by itself. So I'm going to divide both sides by H. Okay, so we have H nu. And so those, oop, nope, I didn't do that right. Let me back up here. I'm going to divide both sides by H. There we go. So those disappear, and you get frequency is equal to E divided by H. And so the value for E, we said in this case they gave it to you 2.961 times 10 to the negative 19th joules. That's a J over Planck's constant, 6.626 times 10 to the negative 34th joule seconds is equal to frequency. And those joules cross out. And then again, that gives you a label of 1 over S, and that should make sense for frequency. You should see the trend here. That's a hertz. And 2.961 times 10 to the negative 19th divided by 6.626 times 10 to the negative 34th. When you divide those, you get a value of 4.4688 times 10 to the 14th. Okay, now that I know what that is, let me just write it in here so I have that to fall back on if I need it later. Okay, so now I'm just looking for this one last piece, frequency, okay? So here we said we had C is equal to wavelength times frequency. We want wavelength by itself because that's what we're solving for. Divide both sides by frequency, and so you get C over frequency is equal to wavelength. So now let's plug those, and I'll do that down here. C is going to be 2.998 times 10 to the 8th meters per second over the frequency, which is 4.4688 times 10 to the 14th, 1 over S equals wavelength. The S's cancel out, leaves you with meters, which makes sense, perfectly viable unit for a wavelength. And then you divide 2.998 times 10 to the 8th by 4.4688 times 10 to the 14th, and you get a value that comes out looking like this, 6.709 times 10 to the negative 7th meters for wavelength. Okay? And then it asks that one last piece of information, right? What do you do if you want a mole of it? Well, this is what the, when they gave us the original problem, they wanted to know the joules in a mole. Okay? In other words, we want to create a unit. They want to take your energy, which is in joules, and they want to convert it into something that's going to be joules per moles. So how do we do that? Well, it's quite simple. We take what our unit is in joules, which was 2.961 times 10 to the negative 19th joules, and we write it over moles. So how many units do we have in a mole? Well, that's Avogadro's number, right? 6.022 times 10 to the 23rd moles, right? And so let me look at this here. That's going to give you, do they want joules per mole or joules over moles? What were they asking for in the problem? Let me take a look at this here. Calculate frequency. What is the total energy in 1 mole? So they probably want joules per mole. Okay, so don't have my calculator here. You could probably do it like this, where you get joules per mole, and then, like I said, let me see if I have a calculator in my desk drawer here. That'll work this out. And I do, so let me punch this out real quick. So you get 2.961 times 10 to the negative 19th equals divided by 6.022 times 10 to the 23rd. Okay. And so they want your answer, it looks like they're looking for it in joules per mole rather than joules over mole. So what they're looking for here is not this unit. My apologies, they want this unit. So they want moles and joules on the same side. So rather, in other words, what this looks like is joules on top of moles, which would be this format here. Okay. Now, if they want joules times moles, joules moles, you've got to put them on the same side. So rather than putting one over the other, we just are going to multiply them. And so what I can do here to fix that is this. And make this a multiplication problem. Okay. And now it's going to end up being joules, moles, and you're actually going to multiply these two values rather than dividing them. And that comes out to 6.709 times 10 to the negative 7th. Okay? And that was the answer if they want it in joules, moles. If they want joules per mole, then you would divide them. So again, it's a little bit of a hair difference when you are looking at the terminology on the sheet, but it is what it is. Okay, going on, a lot of writing on the screen. Let's clear that out and go on to problem 7. 7 is, let's take a look what this says. A photon of light produced by a surgical laser has an energy. Okay, so I'm going to write that down. Energy is going to be equal to 3.027 times 10 to the negative 19th joules. Calculate the frequency and wavelength. So essentially the same thing as the last one. You want the frequency, you want the wavelength, and what is the total energy in 1 mole of photons, blah, blah, blah. So this is exactly like the previous problem. So let's go ahead. Again, we know this, which is Planck's constant. Probably very familiar with that by now. 2.998 times 10 to the 8th meters per second, speed of electromagnetic radiation. And again, you look at these and you see what do you have where. And when you look at this, you have energy, you have Planck's constant, you don't know the frequency, you do know C, you don't know this, you don't know this. So clearly you got to start with that one because you've got 2 of the 3 pieces of information. So again, you're going to have E is equal to H frequency. You want to divide both sides by H, so you get frequency by itself. And you get E over Planck's constant is equal to frequency. And now you plug them in. 6.626 times 10 to the negative 34th joule seconds. Ooh, I'm sorry. I put the wrong value on top. That is H. My bad. Good thing I used a eraser. 3.027 times 10 to the negative 19th joules over 6.626 times 10 to the negative. That is weird. Get that out. 10 to the negative 34th joule seconds equals frequency. Joules cross out, so you get 1 over S. Again, a good unit for frequency. And then when you divide these values, 3.027 times 10 to the negative 19th by 6.626 times 10 to the negative 34th, you get 4.568 times 10 to the 14th. Voila. Okay, so that's your frequency. I'm going to put that in here. 4.568 times 10 to the 14th, 1 over S. Now we're just looking for wavelength. And again, we want wavelength by itself, so we're going to divide both sides by frequency. And so you get C over frequency is equal to wavelength. And again, just like in the last problem, let's go ahead and do that. 2.998 times 10 to the 8th meters per second over the frequency, 4.568 times 10 to the 14th, 1 over S. S's cancel out, so you get meters is equal to wavelength. And 2.998 divided times 10 to the 8th divided by 4.568 times 10 to the 14th gives you 6.563 times 10 to the negative 7th. Now, that gives you your wavelength. Now it asked you, as it did in the previous problem, um, what is the total energy in 1 mole of photons? So again, if you have energy and you know the energy is 3.027 times 10 to the negative 19th joules, and you want to know in 1 mole or per mole how many there are, and in a mole you have Avogadro's number of particles, 10 to the 23rd. So you're just going to go ahead and multiply those again. So you get joules, moles, and when you multiply them, you come out with 1.823 times 10 to the 5th joules per mole. And that's that. Okay, so that's problem 7. Let's go on to problem 8. And problem 8 says, when rubidium ions are heated to a high temperature, 2 lines are observed in its line spectrum at wavelength. So it gives you a wavelength, or 2 wavelengths now. Let's say wavelength A. So I'll call that wavelength sub A is equal to 7.9 times 10 to the negative 7th meters. And 4.2, we'll call wavelength B, is 4.2 times 10 to the negative 7th meters. And so we're differentiating them A and B because obviously you're not going to use them in the same problem because you can only have one wavelength in each of these problems. So what are the frequencies of the 2 lines? So basically what they want to know is what's the frequency of each of these. And so again, we know C for both of these is 2.998 times 10 to the 8th meters per second. And so we're looking for frequency. So if we look back at our formula, C is equal to wavelength times frequency. We want frequency by itself, so we divide both sides by wavelength, and you get C over wavelength equals frequency. So that's going to be the format for both of these. So let's go ahead and set them up. So let's solve for frequency of A. Frequency of A, we'll call this one A because it's in the same line as A, and we'll call this the frequency of B. And we'll call this the frequency of B. And so the frequency of A is going to be equal to C over wavelength. So we've got C here, 2.998 times 10 to the 8th meters per second over the wavelength, which is 7.9 times 10 to the negative 7th meters. And so when we divide those, again, that's M over 1, so those cross out. You're going to have the label as 1 over S. So the frequency of A, when we divide that out, is 3.8 times 10 to the 14th. And now we do the same here, 2.998 times 10 to the 8th meters per second over, this one was 4.2 times 10 to the negative 7th meters over 1. And so again, that's going to be 1 over S, and you divide that out, you get 7.1 times 10 to the 14th power. Okay, so that's the frequency of A, that's the frequency of B. This is actually down the lower range. It's got a shorter wavelength, as you can see. That's a bigger number, so it's a longer wavelength. So this is probably up towards red, and it's going to be down towards blue, and I can show you that in class tomorrow. But that's the bottom line. I'm not going to ask you to do any colors or anything like that on the test. I just kind of want to get you familiar with solving these problems, essentially. But we can certainly relate these. So lower frequency, blue colored, which also yeah, lower wavelengths also. That's interesting. So yeah, we'll take a look at this tomorrow so we can talk about those. But here you've got red, you've got some blue. And so these are frequencies, which the frequencies should actually be a little bit higher than this, I would think, for the blue, because as your wavelength decreases, your frequency has to increase. So I think they've got these backwards. So we'll kind of brainstorm that tomorrow and see. And I wouldn't be surprised if they do, because that happens often in textbooks. So they may have those backwards, so we'll revisit that. And let's go ahead and take a look at problem 9, because that was it for problem 8. Final one. Problem 9. The emission spectrum of cesium contains two lines whose frequencies are, so now they're giving us the frequency as 3.45 times 10 to the 14th. Now they gave it to us as hertz, so I'll put Hz there, but remember that's the same thing as 1 over S, right? And we'll call that frequency A. Frequency B is equal to 6.53 times 10 to the 14th hertz. Hz, that's 1 over S. Alright, so what are the wavelengths? So it wants to know the wavelengths this time. Pop. And the energies per photons and the colors of the lines and all that. Essentially, we're just going to solve for what the wavelengths are. And we could also calculate the energies too, ultimately. Okay, so again, we know frequencies this time. That's something we know. So we got that. We know C. We know H. We don't know wavelengths. We don't know the energies. Okay, so if I look at my two formulas, what do I have pieces to? I got E, H, frequency. Do we know that? Actually, yes, we do know that, because they give them right here. And we know Planck's constant, so we can calculate the energies pretty easily, right? And then C is equal to wavelength times frequency. Do we know C? Yes. Do we know frequency? Yes. Well, we don't know. So this is actually going to work out pretty nice. So let's do the energies. Let's do those first. E, the energy of A, the energy of B. The energy of A is going to be the frequency, which is, Planck's constant, 6.626 times 10 to the negative 34th joules per second, times the frequency of A. So we'll do this, 3.45 times 10 to the 14th, 1 over S. S is crossed out. And so the energy here, let's see if they give that to me. They did it out, yeah, 2.29 times 10 to the 14th, negative 19th. That makes sense too. Negative 19th joules. And then this one here, it's going to be the same H value. And then we're going to multiply it by 6.53 times 10 to the 14th, 1 over S. 1 over S, those cancel out. And then this one comes out to be, for the energy, 4.59 times, looking at the wrong one, 4.33, sorry, times 10 to the negative 19th joules. 4.33 times 10 to the negative 19th joules. Now, so that's the energy of A, and that's the energy of B. Now, so we got these two done. Now we also got to calculate these wavelengths. So again, we've got C is equal to wavelength times frequency, and we know the frequency, but we don't know the wavelength. So we're going to divide these out as such, and you're going to get C over frequency is going to be equal to wavelength. So we got to do that for each. So the wavelength of A is going to be equal to C over frequency. So that's going to be 2.998 times 10 to the 8th meters over seconds divided by the frequency of A, which is 3.45 times 10 to the 14th, 1 over S hertz. Those cancel out. Your label is going to be in meters. So 2.998 divided by 3.45. Right, what did I put here in the bottom? Frequency of A. I'm just checking here in my notes. It's interesting what they did here in the book. It doesn't look right. And No, they goofed. They used a different value in the book. Huh, interesting. Okay, so we'll have to fix that. We'll just go ahead and punch it out manually. So 2.998 2.998 times 10 to the 8th equals divided by 3.45, because that's what they said the frequency was for A, right? Yeah, hertz. Times 10 to the 14th. And so you get here 8.68 times 10 to the 21st. That's probably actually 8.6. Oops. I hate doing that. Keep. That's going to actually be 8.69. I have to correct that. Okay? And then let me do wavelength of B. That's going to be, again, 2.998 times 10 to the 8th meters per second over, and this frequency was 6.53 times 10 to the, did it again. I don't know why it does that. Weird thing. It's a glitch. That's fairly new in the program, because it never used to do that. Must have come with one of the updates. So when we divide this, we get 4.59 times 10 to the negative 7th meters here. Okay. This one looks wrong here, because I'm looking here at these values, 8 and 14, and remember when you divide these you should subtract them. And so, let me punch that in again. 2.998 times 10 to the 8th power divided by 3.45 times 10 to the 14th power. And I'm still getting 10 to the 21st. And that's not right. I don't think that's right. So let me try doing this other one. Let me see what I'm doing. I might be goofing on my calculator. Times 10 to the 8th equals that, divided by 6.53 times 10 to the 14th. Yeah, okay. So this one's going to be, let's see, 8 minus. This one's really going to be to the negative 7th power as well. 8 minus 14 is going to be negative 6, and then when you divide these, because you have a smaller number over a larger number, it's going to make you move your decimal one more spot. And I can't change this again because I had to keep, I couldn't discard the ink change. So it's going to be 8.69 times 10 to the negative 7th. All right, that'll do it. And yeah, it's interesting. They actually punched in some of the wrong numbers here on the solution guide. So, but they give you the right answer. And that's actually the answer they have somehow. But funny enough, the number that they have here is not 3.45 times 10 to the 14th. They actually have, even though that's what it says in the problem, they actually put in, let me go ahead and show you here. They actually put in, so if you read the solution guide, they actually have 7.9 times 10 to the negative 7th there. And that's incorrect, because that's clearly not the value that they gave you for the frequency of A here to start with. So somewhere, somebody goofed. Anyway, this is the right answer, and that's the right answer as well. So basically, this problem, like we said, problem 9 is like problem 8. And we're going to do these in class anyway, so we'll be able to work through these tomorrow. Thanks. Hope you find this helpful, and we will see you tomorrow.